For years, I've been trying to find unique ways to move fluids, specifically air, but water too. I've never been a fan of, fans or propellers. Built lots of interesting air-moving devices, including high-voltage ion thrusters and Tesla pumps with thin discs, but none of them seemed to provide the thrust I needed. This most recent idea was originally based on fish moving through water. Over time, it turned into studying standing waves and how they might be used to move a fluid. Normally, when simulating a fluid, one would use computational fluid dynamics or SPH methods. I had an old physics engine laying around that I thought could be useful for this idea. I wrote this with one of my friends back in my game programming days. I realized that chains of stretch springs between the points in this physics engine have an interaction delay. I thought this could be used to simulate a pseudo fluid for studying acoustic phenomenon and wave propagation. The project initially started as a basic physics engine. There were points where you could connect them with links, and for the application itself, gravity was removed. When multiple links are chained together, it's easy to see that there's a propagation delay. This was an interesting observation and led to a more sophisticated simulation where several points were chained together to see if this could simulate waves traveling through a solid or liquid. Interestingly, it seemed to work well and led to the development of the final simulation. And although these simulations may not be completely accurate, they serve as an interesting starting point for further research. Two sets of moving driver points are allowed to be driven on the top and bottom walls of the tube. The sets are 180 degrees out of phase with each other and add energy to the system. In reality, these would be either piezoelectric transducers or moving walls. They wouldn't be as continuous as they are here. The drivers have three properties: amplitude, frequency, and a neighbor point phase offset. When active, the drivers oscillate back and forth based on the frequency and amplitude parameters. By increasing the frequency, standing waves can be produced between the two sets of drivers. Various harmonics can be seen, with the first harmonic being the one I most studied. There are slight artifacts that alter the fluid at the driver edges, but they're small. When the drivers have a phase offset, the single standing wave now occurs at different points in time depending on the position in the cycle of the individual drivers. For example, the leftmost drivers may be at the stage where the antinode of the standing wave is at a high pressure, and the rightmost drivers are at the stage where the antinode is at a low pressure. these two regions of space have a pressure difference, and this will cause the fluid to move to the area of low pressure for that moment before it destabilizes. As the drivers move through their cycle, these pressure regions form and the fluid moves perpendicular to the driver walls. The frequency and phase are important to maintain this directionality. The frequency for the standing wave must be found before a phase offset is set. This makes things a lot easier. By changing the offset, the traveling pressure waves change size, speed, and shape. This type of pseudo-solid state fluid pump can be reversed and the amplitude can be increased easily. Although these waves travel perpendicular to the drivers can be made to travel very fast, the fluid particles themselves, they may not have enough time to accelerate, and the waves may pass through them, similar to sound waves. This will cause particles to oscillate back and forth instead of move with the traveling waves. For this to function as a propulsion device, the waves likely need to be slow enough to accelerate the fluid. I don't know at this time if low-frequency, non-acoustic waves will produce the effect, but hopefully they will. The applications are pretty interesting. They include micropumps for medical devices, boat or submarine propulsion, and potentially aircraft propulsion, although the fluid density may be too low for such an application. Alright, well that's my video. Thank you, and hopefully there will be more updates soon.